Hey there, man, Alejandro. Welcome back for day 207 of me doing the Daily LeetCode challenge after I reach 1 year's worth of good contributions here on GitHub. So today is also for February 8th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 2349, design a number container system. Design a number container system that can do the following. Insert or replace a number at the given index in the system. Return the smallest index for the given number in the system. Implement a number. Okay, the very first thing that comes to mind is, okay, if you want to place things in place at a certain index, use a linked list. If you want the smallest index, just keep track of a min heap of all the numbers, right? Implement the numbers containers class. Initializes this. Fills the container at index with the number. If there's already a number at that index, replace it. We can also use a hash map. Or no, because then it would require updating all the indices. Yeah, no, we need to use a linked list. Oh, we can use a linked list, but map all the indices to the node. Okay, yeah. Int find returns the smallest index. Or for the given number. Oh. I see. Right, so as you change indices of numbers, you're going to mess things up. All right, okay, that's going to be the hard part of this problem. Okay. 10 to the 5 calls, yeah, change and find. Dang, so at most 10 to the 5 calls, so the amortized complexity needs to be O of 1. Okay, well, putting something, yeah, change can be made O of 1 with a linked list. Then int. Yeah, that's annoying, right? Yeah, okay, that's kind of annoying. Where if you put something in place at a certain index, you've moved everything to the right, and you still want to know what is the smallest index of a number. It's pretty darn annoying. I will not lie. Yeah, my intuition tells me, we can definitely have a linked list where we have a hash map of all the indices. But yeah, the question remains, when you insert something, how do you keep track of the fact that you just updated the smallest index for every other number, right? Because you can't do O of n time every single time because there's 10 to the 5 calls made. 46% exception rate. How many people? 1982. Index number. Yeah, this is interesting. I can't keep logs of, like, I added something at an index or anything bigger than that. Because otherwise it's just like, ugh. And you somehow update state in O of 1. It's like, the problem is when you add a number, you're gonna end up messing up all the indices. No, even if I collect them all and then the next find call I push them all down in O of n, still might be O of n time per find call. Unless I can argue that it's at most 2n in terms of amortization. Right? Almost like, let's say, okay, when I add something at index I, then I say, okay, anything that's index I plus 1 will get plus 1. But no, when I add something at index j that's greater than I, then only things that j I don't want to plus 1 it. Oh my gosh, this is annoying. Okay. I could also have a heap, right? I could also have a heap. Mate, how do you not make it oven in a find? How? Okay. This is very interesting, actually. This is not sure your problem at all. The problem is simple, not easy. Oh! You replace it! You don't shift everything. Oh my gosh. Okay. The problem becomes a lot simpler. You don't shift everything. Okay, you replace it. Well then, ladies and gentlemen. A little bit easier now. Okay. So yeah, you're not going to deal with shifting. Okay, insert or replace the number at the given index within the smallest index for the number in the system. So yeah, here we'll just say self.index to num is equal to this. Here we might do self.num to indices. Now let me think here. Okay, the problem is definitely much easier. We just got to do a tiny bit of thinking here. We don't necessarily want min heaps, right? What I care about is when I remove a numbers index. Maybe I keep track of a min heap. And if stuff is invalid, then it's invalid, right? So here we'll say actually, yeah. We'll say this. If index not in self.index to num, then we'll say self.index to num of index equals number return. Otherwise need to replace current number. We could delete, or we can just choose not to delete stuff in here, right? Like what I'm saying is, what if we did something like this? Self.num here we'll do push index, right? And here we'll say while min heap dot num to indices of num min heap of 0. Well, it is not the case that self index to num of min heap of 0 equals number heap q dot heap pop while length Yeah, it'll be a reference, right? So yeah, while length of min heap is greater than 0, and this heap hop from the min heap. Return heap of 0 if length of min heap greater than 0, else -1. Right? Something like this. Number. Okay. Number. Okay. Okay, let's accept it. Let's submit. And there we go. Completion streak 207 days. Consistency is key. See ya tomorrow. Okay, yeah, this problem is definitely a lot easier when it says replace the number at an index, not like, you know, shift everything so on, where, you know, there's only at most 10 to the 5 columns, because it was going like, mate, no matter what you do, you have to, you gotta sacrifice something here. So yeah, when I saw the words replace it became definitely a lot easier to do. Okay, here we'll just do this. Yeah, so here we're just, yeah. Dict of lambda. Actually, it could just be a dictionary. Here you can do while min heap. Yep. Yeah, let's bring everything a little tighter here. Yeah, okay. I mean, this is fun to me, right? The only thing is that, like, you know, I might be pushing indices, and when I change things, okay, wow, 99 ms beats 89.71%. So we probably have, you know, an optimal-ish type of solution. The only thing I'd have to think about is, like, okay, whenever you change, would you want to delete stuff from the heap, right? Because here it's kind of convoluted to have to do log and pops every single time. But then otherwise, like, you know, if you keep it as a set, then yes, pops are very easy. But then finding the min is linear, and if you keep track of both, then you still have to, like, you know, keep popping until, like, you know, you have something on the set. So you might as well just do the work. Like, you'll have to do the work somewhere, somehow, anyways. You might as well just do it lazily, only whenever you need to. So I guess it's fine to leave it as is. This is nice. Okay, so as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, essentially, we want to design a number container system, which allows us to insert or replace a number at a given index in the system and return the smallest index for a given number in the system. So basically, we have a change function, which gives us an index and a number, and we essentially want to say, hey, the value at index should be number, right? Which means that if there's currently already a value at index, which is what stopped me at the very beginning of the problem, we should replace it, not add a new one and continue the list and so on, right? It's not like insert. It's not like, you know, insert a new number at index. It's literally like, okay, make the number at this index this number. Otherwise, if there's already a number at that index, replace it, right? And find here essentially says, okay, return the smallest index of a number, and if there is no such number, then return -1, right? And so that's kind of the point. And the way that I did this is essentially, it's like, okay, we're gonna have two hash maps. One is gonna map indices to the numbers at those indices, right? So it'll just be a nice little hash map there. And another one, it'll essentially be it'll map numbers to a min heap of their indices, right? Lists are min heaps. Just to make it clear, right? Essentially, it'll map numbers to list of the indices, but the list will essentially be min heaps. They'll be heapified, right? Well, initially they're empty, so they're already heapified, and whenever we push and pop stuff, we'll do it via heapq.heappush and heapq.heappop, which are log n operations, right? And that's going to be the idea. And that way, whenever we want to do our change function essentially says, okay, set the value at index to be number, right? So here we'll say, okay, in our self.index to num, we'll say, okay, index to num at index will be the number, right? But now we just said, okay, at this index, we now have this number, right? So here for num to indices, we're going to say, okay, in self.num to indices, we're going to say, okay, for number, there's now a new index that it's at, right? It'll be index, right? Whether or not it already existed in there, right? So the point is that we might have stuff in the main heap. We might have way too much stuff in the main heap, right? Let's say we add something into the main heap and then we immediately replace this index with another number. We won't make any effort to essentially delete it here, right? So whatever number was already here, whatever number was already at this index, we're not going to bother deleting that from the list of indices for that number in self.num to indices. And you'll see that why later. But the point is that, like, you know, our min heaps might have invalid indices in there, right? But that's not the problem. That's not the point here. For here, we're just saying, okay, self.index to num of this index is equal to number. That's obviously the number of this index now. And we're going to push, okay, we're just going to pretend that, like, you know, this is we're going to say, okay, this number now has a new index at this current index that we just added the number to, right? So that's all it is for the change function. Now for the find function, essentially we're going to say, okay, let's grab the min heap of indices for the number that we're given, right? So for this number, we're going to say self.num to indices of that number. And here I say just dictionary is equal to self.index to num, right? So we map indices to numbers here, a hash map that will map an index to the number at that index. And here we'll say, okay, we're conscientious of the fact that in our main heap, we might have invalid indices. We might have indices in our main heap that no longer point to our number because they could have been replaced via more change functions, right? So here what we'll do is, okay, at our main heap, at index 0 will always be the smallest index, right? Out of our min heap, the value at index 0 is always the smallest element in the min heap, right? So what we'll say is, okay, let's grab the smallest index, which will always be min heap at index 0. And if that index, we point to the number that is there, while it is not the case that it is the current number that we're looking at, that means it's a stale index, right? This number is no longer at this index that we're looking at here, right? So we'll grab the smallest index that we currently say that we have the number for, and here we'll say, okay, we'll map that index to the number that's actually at that index. And if that number is not the current number that we're looking at, that means that's like, okay, it must be a stale index. So we're just going to keep popping from the heap over and over and over and over and over until we find the smallest index that happens to be the number, right? And we're also going to keep doing this as long as, like, you know, min heap is not empty, right? Because at some point it could be that min heap is empty. So if we ever exit this while loop because min heap is empty, that means there's no indices for that number, in which case we'll say, like, you know, if length of min heap is greater than 0, return this, otherwise return -1, right? So if the length of the min heap is 0, either because it was 0 to start with or because we popped stale indices and it no longer exists, if there's no more instances of that number inside any index, then we'll return -1, right? Otherwise, if we at some point finally find an index that is the smallest index, where the index to num mapping is indeed equal to the number that was given to us here, then we'll finally return that one, right? So once we're done with this while loop, we'll return the smallest index, right? Min heap of 0, if the length of min heap is greater than 0, otherwise return -1 because there's no more indices that have this number. And there we go. Hopefully that solution makes sense. And yeah, that's pretty much it for how I was able to solve the problem. So hopefully that solution makes sense. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any shape or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.